Okay, so now let's say we are going to deal with only the conjugate base of a weak acid. Now, you can get to a conjugate base of a weak acid in two different ways. We could either take HC2H3O2. It's going to break down into hydrogens and acetates. And then all you're going to do is add enough hydroxides in, use all that up. It's going to keep shifting over. All this will get used up. And at the end of the day, all we're going to have left is acetates. Or I could, like in the problem we're going to do, I could add sodium acetate or potassium acetate or whatever acetate you got. And then when this gets put into water, what we're going to have is we're going to have sodium ions and acetate ions. And so whatever the situation is going to be, whether we neutralized out all this acid or we just simply added this guy in, whatever the situation is, we're going to end up with a solution that has just simply the acetate ions in it. Now, if we just, and it's horrible looking, if we just had acetate ions in it, remember those acetate ions will function as a base. The anion of a weak acid will function as a base. So in this situation, I have 2 moles of sodium acetate. It's placed in 1 liter of solution, and so I've got a 2 molar acetate ion solution. Okay, so that's just one way of doing it. I will recognize that acetate is a conjugate base. And when we say conjugate, conjugation means to go together. It's a conjugate base of acetic acid. So it will act as this. Acetate ions plus water is going to make acetic acid undissociated plus hydroxides. So think of this hydrogen coming over, joining that, and then we'll lift over those hydroxides. Now, what we're going to have is, once again, 2 molar minus X, 2 minus X. We're not going to put water in there because it's a liquid. 0, 0, gain X, good to go. Now, if you remember from the last problem, Ka is 1.8 times 10 to the negative 5 for acetic acid. Ka times Kb is equal to Kw. You can kind of think of the hydrogen ions times hydroxide ions is equal to Kw. Well, the Ka times the Kb is equal to Kw. So take my Ka, divide it into my Kw, voila, I get a Kb. Yay. Okay, now what we're going to do is we're going to come over here. We're going to have our equilibrium expression for the base, which is going to be the undissociated acid hydroxides over the anion. Kb is equal to x squared divided by 2. X squared divided by 2. Come down here. 5.55 times 10 to the negative 11 is equal to x squared over 2. Okay. Now, the hydroxide ion concentration is 0.000033 molarity. Okay. Now, if you remember once again, in normal water, 1.0 times 10 to the negative 7. So 0.1, 2, 3, 4, 5, 6, 1 molar hydroxide. That's what's normally in water when water is basic. Now we've got 1, 2, 3, 4, 3, 3. So you can see the hydroxide ion concentration is significantly higher. And we come on down. Kw is equal to, so that's a hydroxide ion. Kw is equal to hydrogen times hydroxides. Put that guy there. Kw. Hydrogen ion concentration is 3.03 times 10 to the negative 10th. Wow, that makes sense. Since this guy is now in greater quantity, this guy's in lesser quantity. Yay. Negative log of 3.03 times 10 to the negative 10th. My pH is now 9.5. So this makes sense. I add the anion of a weak acid to water. The pH shows that it's actually basic. It's above 7.